In this video lecture, we're going to see a very useful tool in the probability theory, which is that events can be approximated in a generating algebra. First, we will discuss what it means to approximate. Then we'll give a proof of the approximation theorem using the notion of outer measure. And then we give an alternative proof of the same property using the pi lambda theorem. Let us start discussing then the notion of approximation before we can state the main theorem. The difference between two sets is usually represented by what is called the symmetric difference. So this is a way to measure, to quantify how much two sets or two events, if it is a probability space, how much they are different. This is defined as the set of points which are in A but not in B, or the points which are in B but not in A. So it's the collection of both these two types of sets, either in A not B, or in B and not A. This notion of difference satisfies something which is analog to the triangle inequality. And by that we mean if we can compare A and B, and we can compare B and C, we can use that as an upper bound for the comparison between A and C. This is what is written here. This is the upper bound part. So if we have a control on the difference between A and B, and we have a control on the difference between B and C, we can use that to get a control on the symmetric difference of A and B. So here I'm asking why, and as you have seen already, each time I ask why during a lecture or in the lecture notes, it means it's an exercise for you to prove the stated property. Another property the symmetric difference has is the symmetric difference between the complement of two sets is the same as the symmetric difference between these two sets. I ask you to write a proof for yourselves as an exercise. And finally, if we take a union of sets, a finite union of sets, so if that works with two, you can extend it to finitely many. The union of sets, and you want to find the symmetric difference between a union and another union of sets, then this is bounded from above by trying to match one set from each union to the other set, taking that, the corresponding symmetric difference, and then taking the union of these two symmetric differences. And now the main theorem of this video lecture, now we quantify approximation. And how do we quantify? Well, we want now to talk in terms of numbers. Then we have a measure, and that, let's say that is a probability measure. So we interpret these events, these sets as events. So the probability of the symmetric difference between two events is exactly the probability that one of them occurs but not the other, whatever one. And the theorem here, it says if we have an algebra of sets, an algebra of sets of a subsets of a sample space omega, and all these sets in this algebra, of course, as members of the sigma algebra in this probability space, then for events in the sigma algebra generated by that algebra, they can be approximated by events in the algebra. And being approximated is expressed mathematically in terms of for every epsilon, no matter how small, we can always find some A in the algebra. So this A will depend on epsilon. This A will depend on what is the set B in the sigma algebra generated by this algebra that we are considering. Okay, but then there exists some A such that A is a good approximation for B. And by good, we mean it approximates up to that required level of precision.